Let's welcome Dr. Mark McCaughrean.
Well, thank you very much. It's a great privilege and pleasure to be here in Beijing today to talk to you about one of the most ambitious, complex scientific projects ever put together, the James Webb Space Telescope. This is a collaboration between the US Space Agency, NASA, European Space Agency, and the Canadian Space Agency, and has been over 20 years in development. And I want to give you a bit of a picture today of why we're building this observatory, what we expect it to do scientifically, and where we are in terms of the status. But let's start back at the beginning. For hundreds of thousands of years, human beings have been staring up at the night sky and seeing a band of light across that sky, which we now know to be our Milky Way galaxy, a collection of 200 billion stars, of which we are but one small, insignificant solar system part thereof. You can also see in the top left corner of the picture here two of our neighbor galaxies, the Large and Small Magellanic Clouds. And we now understand that even our Milky Way is just one of hundreds of billions of galaxies throughout the entire universe. To learn this and to understand this, we've built amazing machines like this. This is just one of 4 of very large 8-meter diameter telescopes in the Chilean desert run by the European Southern Observatory. And we build these massive machines and we operate them together to probe deep into the universe, as you see here, also in combination with the small telescopes to the side. We usually put these telescopes on the tops of tall mountains. This is Mauna Kea in Hawaii, over 4 kilometers high, above much of the atmosphere and above much of the weather which you see below. And just a brief anecdote, I was actually married on the summit of this mountain. A very breathless occasion, you might say. Thank you. But even Mauna Kea, with its fantastic position on an island in the middle of the Pacific Ocean, is not perfect. There are days and nights when Mauna Kea is shrouded in cloud, and the observatories can't open, and we can't use them to study the universe. Even on clear nights, the sky, as seen from the ground, is not perfect. You can see here the Milky Way rising as a column in the center of the picture, but you also see the glow of towns and cities beneath the clouds, reflecting off the clouds, and also a greenish glow on the horizon, which is atomic oxygen high in the atmosphere of the Earth. And that glow imposes a limit on how faint we can see things from the ground. You also see a red glow there to the center left, which is actually a volcano. And not all observatories have volcanoes erupting at the time when you're taking pictures. But in this case, you can see that. And then another effect which we have on the ground, which disturbs what we do with ground-based astronomy, is atmospheric turbulence. Here's a picture of the moon taken from the ground, shimmering as turbulence in the atmosphere moves the surface of the moon around, apparently. And in long-duration exposures, long-duration pictures, that will blur the image out and reduce the resolution, make it worse than we can do theoretically with a telescope of a given size. Now, in recent years, we've managed to improve upon that, in particular by using laser systems to provide artificial stars in the sky high above the telescope, and then use that to correct the turbulence. That's working extremely well, but still isn't perfect. So ultimately, the best place to do much of astronomy is in space. And in April 1990, NASA and the European Space Agency launched the Hubble Space Telescope on the Space Shuttle Discovery, which you can see here. And the Hubble Space Telescope has now been in orbit for over 28 years, returning enormous amounts of scientific data and new understandings of the way that the universe works. Hubble is just 400 kilometers above the surface of the Earth and can be visited by astronauts. In fact, it had to be visited by astronauts soon after its launch to repair the ill-formed main mirror of the telescope. But it was possible to do that by putting in corrective optics, and then new scientific instruments and other new components have been added to Hubble, and it's still working very well today. We had a minor hiccup a couple of weeks ago, but it's now recovered and is working well. And this is just one image taken by Hubble, one of many thousands which you will have seen. This is a region in Carina, the constellation Carina, where you can see clouds of gas and dust which are forming new stars today, stars which might be only 1 million years old. That seems old, but compared to the age of our sun, 4.5 billion years old, that's the same as a 3-day-old baby compared to a middle-aged person. So we're seeing very young stars in these regions being born. There is, however, another reason to go into space, and that is that the atmosphere of the Earth is not transparent at all wavelengths. Visible wavelengths can come through the atmosphere. It's transparent all the way down to the ground. That's how we can see the stars with our eyes. But there are many other wavelengths, as you can see here, high-energy wavelengths in the gamma ray and the X-ray, which are the atmosphere is totally opaque, and we need to put satellites above the atmosphere to observe them. And then at longer wavelengths, in the infrared, you can see also that the atmosphere is mostly opaque. You can ameliorate some of that by going to high altitudes in aircraft, but ultimately, you want to be in space. And then at very long radio wavelengths, the atmosphere becomes opaque again. Now, the region we're particularly interested in with JWST is right here, in this rather messy region where some wavelengths can be measured from the ground, but others can't. And why are we concentrating on this region? Well, let's look at a spectrum of light coming from an object roughly 3,000 degrees in temperature. You can see that there's a lot of light at visible wavelengths, where the rainbow is there. There's a bit of light to the ultraviolet side, and a lot more light at longer wavelengths. Now, this is a star. This would be a star which is roughly half the temperature of our sun, a red dwarf star. But if we change the temperature progressively lower and lower, so to start with, the green curve there is 300 degrees Kelvin. That's roughly room temperature. It's the temperature we're all at here in the room. Then you see there's very little light, if any, in the visible at all. And then as we go to cooler temperatures, 30 Kelvin, that's minus 243 degrees centigrade, would be the temperature of young star-forming regions, the clouds out of which stars are born. There's no light at all in the visible. And then the cosmic microwave background, the leftover light from the Big Bang, is at just 3 degrees above absolute zero, and all of its light is at long wavelengths. So that's why when we want to study phenomena which are cool, young objects being born in the universe, they haven't yet developed their full heat, we need to go to the infrared. And this is a region called the Orion Nebula, well known to many people. Amateur astronomers take lots of lovely pictures of this region. But this is a visible wavelength picture taken by Hubble. So if we now want to look inside the gas and dust and see where the young stars are being born in this nursery of star formation, we need to go to the infrared. For two reasons. One, because the objects are cooler, but also because dust, which there's plenty of in this region, blocks much of that light. So now we're going to move to the near infrared, and we suddenly see many young stars being born in this region, things you just couldn't see in the Hubble image at all. So that's one reason we want to build an infrared telescope, to look at star formation and planet formation. The other reason has to do with this picture here. This is one of the more famous pictures taken by Hubble. It's what's called the ultra-deep field. It's months-long worth of integration of taking pictures at one point on the sky and measuring the light from galaxies. Everything you see in this picture is a galaxy. The big ones are relatively near to us. The more distant ones are the smaller ones. And of course, when they're more distant, they're further away, and that means that it has taken time for light to travel to us. We're seeing back in time. We're actually looking further and further back towards the birth of the universe 13.8 billion years ago. And because the universe is expanding, the light from those stars, which were born in the early universe, has been redshifted, stretched out. And so when we go to a redshift of 3, which is equivalent to looking back about 11 billion years, 11 to 12 billion years into the past, you see the light is moving to the red. There's not much left in the visible. And then when we go to redshift of 10, which is roughly where we think a few 100 million years after the birth of the universe, stars and galaxies started forming, there's very little light in the optical. And in fact, everything is worse than that, because of the stretching of the universe, they're also much fainter than they would be if they were nearby. So to study these sorts of objects, we need to build an infrared telescope in space. So let's talk about the Hubble Space Telescope, which we've had in orbit for 28 years. You can see there's a person for scale right at the bottom there in the reflection. It's a rather big observatory. It's 12.5 tons. It has a main mirror 2.5 meters across, and it operates at room temperature, roughly. It was launched on Discovery, as you saw earlier. The James Webb Space Telescope is completely different. It is a much bigger telescope with 18 segments of beryllium, which make up one mirror 6.5 meters across. But it only weighs half as much as Hubble. It's only 6 tons. And it also has to operate at much lower temperatures than Hubble, because Hubble is giving out infrared light. It's warm, like we are in the room. So to avoid blinding yourself with a telescope that's emitting infrared light, you must make it cold. And so we will cool JWST down to temperatures around minus 223 degrees centigrade. And we do that with this enormous sun shield, which you see under the telescope, which allows us to block the sunlight and lets the telescope cool down. So let's look a little bit more in detail at this machine. You can see the giant mirror there with its 18 beryllium segments, the secondary mirror, which then reflects light into where another optic system is, and on the back of the telescope, all the scientific instruments. And there are 4 main instruments built in Europe, the United States, and in Canada. We have to shield that all with the sun shield, hide all of the warm stuff, all the cold stuff on one side of the sun shield, and then on the warm side, we have electronics, we have radio transmitters to beam the data back to Earth. We started looking at how we could build this machine more than 20 years ago, as I said, and there's been a lot of technology developed, a lot of new inventions had to be made in order to make this observatory possible. This, for example, shows some of the test mirrors being put into a giant cryogenic chamber at very cold temperatures to make sure they would keep their shape when they were changed from room temperature down to very cold temperatures. The whole telescope was then assembled, which you can see here in the clean room at NASA's Goddard Space Flight Center. And you can see the scale with some of the people here. This is a truly enormous machine. And of course, that machine is no use, on the other hand, when you collect the light, you need to send it somewhere. And we have built these 4 scientific instruments, very complex machines with mirrors and lenses and detectors, all of which will take images, spread the light out into a spectrum, and also have the capability of blocking the light of nearby stars to see if there are planets nearby. So all of the instruments were packaged together. This is the European instrument near spec being put on the side of the big instrument package. The whole unit was then dropped into a giant cryogenic chamber, and for several months, the science teams were testing the instruments and making sure they would work at these very, very low temperatures in a vacuum. Then the instrumentation was attached to the telescope itself, integrating that together. You can see it being dropped there, descending on top of the back of the telescope, and then being attached. And then the entire telescope was taken to Johnson Space Center in Houston and put into one of the world's largest cryogenic chambers. This one you see here, in fact, was used to test the Apollo spacecraft in the 1960s, and has been upgraded to be used to test the James Webb Space Telescope. You can also see something very important here, is that JWST is too big to launch into space unfolded. So it actually has to fold up into a much smaller package in order to be launched into space and then be unfolded. And I'm going to show you how that works in a moment. But the critical component that's missing from this picture is, of course, the sun shield. And this giant sun shield is the size of a tennis court, 22 meters long, and is made of 5 individual layers of very thin metallic film, less than the width of a human hair, the thickness of a human hair. And all of these have to work together to shield all of the sunlight on one side and block it to make sure that the telescope on the other side can get cold. Here's the sun shield being all packaged up and folded together for flight. And in fact, more recently this year, we had some problems here because the way that the sun shield is held down for launch is with various bars and nuts and bolts to hold it all in place before we fly the telescope. And when we put the telescope or the sun shield into a chamber to vibrate it to test whether it was ready for launch, some of the nuts and bolts fell off. Unfortunate, but it was good that we measured that on the ground rather than in space. So we're now repairing that part, and that's led to some delays in JWST. But we understand the problem and are fixing it right now. So the full-scale JWST looks like this. You can just about see some people here along the bottom for scale. It's a huge observatory when it's fully deployed in space. But as I said before, it's too big to fly in that form. So we package it up into this container here. We fly it around the United States in order to get it integrated in various ways, and it will finally go on a ship and sail to French Guiana on the eastern coast of South Africa, which is where the European Space Agency's spaceport is, and we will launch it on an Ariane 5 rocket, the largest booster that we have in Europe. And it's a very successful rocket with over 100 launches behind it, so we are confident that this part will work, and we're looking forward to that being in 2021. So let's just look at what has to happen next. The telescope is folded up into this package, and as it goes out to its point 1.5 million kilometers from the Earth, it starts unfolding. It takes 15 days. We unfold the solar array to get some power. We push the telescope up away from the spacecraft and then start unfolding the sun shield. Slowly but surely. It takes much longer than you see in the picture, of course. And then we tension the sun shield to make sure it's all in the perfect shape. We deploy some other parts of the spacecraft to keep it balanced in space, and then put the main secondary mirror over to reflect the light from the primary mirror, and then unfold the wings to make the full observatory that you see there. And the place we're going to go is the L2 point, 1.5 million kilometers away from the Earth, which is just 1% of the distance that we are to the sun. But it's a place that's stable. It means that the observatory will follow the Earth around as it goes around the sun once a year. And that lets us keep the sun shield on one side, pointing at the Earth and the sun, and on the other side, the telescope will be cold. So you see here, when we fly out to the L2 point, the observatory will orbit around the L2 point slowly and keep the sun shield always pointed towards the sun and the Earth to block away their radiation. So let's just conclude by reminding ourselves of what some of the science is. JWST is going to study planets in our own solar system, and also small bodies, the moons of those planets. There's lots still to be learned about how the solar system formed, what its constituent parts are, and how they evolved over the 4.5 billion lifetime of our solar system. Beyond our own solar system, of course, we're going to be looking at places where new stars are being born, with new planets being born around them. And all of this happens at infrared and longer wavelengths. So that's why JWST is so important. These have not heated up enough yet, these regions, to give out visible light. But there are also stars with planets orbiting around them well beyond our solar system, which we know about, so-called exoplanets. And we know of many cases where those planets pass in front of their parent star, and when they do that, they block a little bit of light from the star, and we can then use that blocking, that change in intensity, to measure the spectrum of the planet and look at its atmosphere. And has that atmosphere got traces, possibly, of life? So JWST will be looking intensely at many known exoplanets. We'll be looking at star-forming regions like this, again in Carina, where there are thousands of young stars being born. And on the largest scales, we'll be looking at the formation and evolution of galaxies over cosmic time. This is a large-scale simulation showing how galaxies slowly merge together and form larger structures over cosmic time. And we will be analyzing galaxies as we look out further and further away, back in time. And this, again, is the Hubble ultra-deep field, which you can see as we sweep across it. Every one of these galaxies has hundreds of billions of stars. There may be planets orbiting those stars. There may be life on some of those planets. And the James Webb Space Telescope will help us probe many of the mysteries that remain about our universe from the very origins of the stars and galaxies 13.8 billion years ago down to what's happening right today in our own Milky Way galaxy. So let me finish with one little short film to show you where everybody will be very nervous in 2021. And that happens because we have to launch this amazingly complex machine and put it into space on a barely controlled explosion called a rocket. Just a few weeks ago, we did that with our Bepi-Colombo spacecraft, a collaboration with Japan, which has launched to go to the planet Mercury. So I just thought, as a rocket scientist, I would leave you with a film of a rocket being launched.
5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage 2EAP, décollage.